Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.3. Calculating Limits.
Lesson 3. Limits of piecewise functions and the Squeeze Theorem.
The next thing we're going to do is look at a limit that involves a piecewise function. Well, we've already done this kind of limit before in the previous section. However, in this case, we are going to be looking at the limit of a piecewise function done algebraically instead of having to draw the whole graph like we did in the last section. So here I have a function f of x that has one rule, 5x minus 1, whenever the input into the function is greater than or equal to 2, but an entirely different rule, f of x is computed using x plus 2, whenever the number I'm putting into the function x is less than 1. We are asked to find the limit as x approaches 2 of this function f of x. And notice that the place we're asked to find the limit at, x equal 2, is exactly the place where the function switches rules. Okay, well, let's try to do this without having to graph it, because that's a lot of work, although I will show you the graph at the end just so that you have some feeling for what was going on in the problem. We want to find the limit as x approaches 2 of f of x. That means we want to find the overall limit, the limit as x approaches 2 from both directions. But remember that the overall limit exists if and only if what is true? Well, we said that the overall limit exists if and only if the limit from the right and the limit from the left both exist and are equal to one another. So the overall limit exists if and only if the limit as x approaches 2 from the right of f of x exists, and the limit as x approaches 2 from the left of f of x exists, and those two limits are equal to one another. So the overall limit exists if and only if the one-sided limits are the same. The left and the right-hand limits exist and are the same. So let's go ahead and see if we can find the limit from the right and the limit from the left separately. So I'm going to start by saying I want the limit as x approaches 2 from the right through values that are a little bit larger than 2. So don't forget that if we are approaching 2 from the right, we are looking at x values that are a little bit greater than 2. Well, for these x values that are larger than 2, what is the definition of this particular function? If we go back up to the rule, it says when my x value is greater than or equal to 2, in this case x is greater than 2, so we're talking about this portion of the domain. For those values of x where x is greater than 2, we are supposed to use this top rule. 5x minus 1 is what we use for f of x. So because my inputs are coming in from the right through values that are greater than 2, when I say, well, what is f of x, I have to use the top rule. And the limit as x approaches 2 from the right of f of x then is the same as the limit as x approaches 2 from the right of 5x minus 1. And again, that's simply because that is what f of x is equal to when my x value is something greater than 2. Well, how do I find that limit? This function that's in here now, 5x minus 1, what type of function is that? That is a polynomial. So in order to find that limit, I get to use direct substitution. I just replace the x with whatever value x is approaching. And remember, this works whether we're doing an overall limit or a one-sided limit. In this case, it's a one-sided limit, but I just go ahead and replace the x I see with the number it's approaching, namely 2. So I would end up with 10 minus 1, that would be 9. And that would be the limit of my function f of x as x approaches 2 from the right-hand side. Okay, what about when x approaches 2 from the left? What can I say about f of x in that case? Well, remember, if we're approaching 2 from the left, we're approaching x through values that are less than 2. So I have to ask myself the question again, what is f of x for those particular inputs? Well, when x is less than 2, I'm right here in this portion of the domain, and for those values of x, I am supposed to use the bottom rule for f of x. So f of x is the same thing as x plus 2 for these values of x. So what can I do now? I can go ahead and say, well, this then would be the same as the limit as x approaches 2 from the left, and I can replace f of x with the bottom rule, x plus 2. So for x less than 2, f of x, we use the bottom rule, is the same thing as x plus 2. Well, how do I figure out that limit? Again, notice that x plus 2 is just a polynomial, and because it is a polynomial, that means I get to use direct substitution in order to evaluate it. So x is approaching 2. It happens to be from the left, but all our limit laws work even when we are doing a one-sided limit. So all I do is replace x with the number it's approaching, namely 2. So this would become 2 plus 2, or 4. The limit of f of x as x approaches 2 from the right is 9. The limit as x approaches 2 from the left is 4. What about the overall limit? That's what I was actually asked to find up here. I wanted to know the limit as x approaches 2 from both directions of f of x. So when we ask what is that equal to, well, remember what we discussed earlier, the overall limit exists if and only if the one-sided limits exist. They do. One of them is 9 and one of them is 4, but they also have to be equal to one another. So the overall limit exists if and only if the one-sided limits exist and are the same. Are they the same in this case? Unfortunately, no. These two things are not equal. 9 is not equal to 4. So what do we say about the overall limit? Well, the overall limit as x approaches 2 from both directions of f of x does not exist. And that's just because the one-sided limits are not equal to each other. Well, I'm just going to add on here the graph of this function. You could graph it yourself. Each half is really a straight line, but we only use a portion of the line. For values that are to the right of 2, we use the line y equal 5x minus 1. For x values that are to the left of 2, we use the portion of the line y equal x plus 2, corresponding to those x values. And you end up with a graph that looks something like this. I'll just put it up quickly for you so that you can see. And here we can see maybe a little more clearly what's happening. As I approach 2 from the right-hand side, I go up to the graph and over. Oh. So let's go ahead and just quickly look at the graph of this function. We didn't need it in order to find the limit, but just to sort of connect with what we did when we were finding these limits of piecewise functions in the last section, I thought I would show you the graph. You can graph it easily yourself. It looks like the straight line y equal 5x minus 1, but only the portion of the line that corresponds to points whose x-coordinates are greater than or equal to 2. That's this half line. And then it looks like the line y equal x plus 2, but only the portion of the line corresponding to x-coordinates that are less than 2 to the left of the 2. So that's this half line down here. And if we had been asked to find the limit as x approaches 2 of this function from the graph, remember how we would have done it. When we choose a value of x that's a little bit greater than 2, we would go up to the graph, which is up here, over to the y-axis, and the closer I get to 2 from the right side, the closer it looks like the outputs are getting to the number 9 on the y-axis. And so the limit as x approaches 2 from the right of my function is equal to 9. If I were to look at the limit as x approaches 2 from the left, I would go up to my graph and over to the y-axis, and the closer I get to 2 from the left, the closer my outputs are collecting around the number 4. And so the limit of this function as x approaches 2 from the left is equal to 4. Now, if I were to ask you about the limit as x approaches 2 from both directions of f of x, and you were just given this graph, you would say, well, the limit does not exist because the y values are not collecting around one number on the y-axis. They are collecting around two different numbers, 4 as we approach 2 from the left, and 9 as we approach 2 from the right. The one-sided limits exist, but the overall limit does not exist because those two one-sided limits do not match up. Okay, let's go ahead and look at the next page. And here we have some other limits that are similar to the one that we just did. We're given this example. We're asked to find the limits or prove they do not exist. And in this case, although it's not written as a piecewise function, it is a function that involves an absolute value of x. And you might remember that the absolute value of x can be written as a piecewise function. It's equal to x whenever x is greater than or equal to 0, and it is equal to minus x when x is less than 0. We'll review that as we go through. In part A, I'm just asked to find the limit as x approaches 0 from the right of the absolute value of x divided by x. So remember that if we are approaching 0 from the right, we are looking at values of x that are greater than 0, to the right of 0. What does that mean? It means that my x is something that is a positive number. So keep that in mind, x is going to be positive. Well, what can I say about the absolute value of x if I know that the x itself is a positive number? If x is something like the number 6, the absolute value of 6 is just equal to 6. I can just take the absolute value signs away. So if I know for a fact that x itself is a positive number, I don't need the absolute value signs. Absolute value of x is just equal to x. So for these x values that we're limiting through, for x being positive, I could rewrite this limit and say this is the same as the limit as x approaches 0 from the right of, and this absolute value of x that I have right here can be replaced with just x. So that can be replaced with just an x. But it's because the x we know is something that is a positive value. Okay, the denominator of my expression is just x, so I'm just copying that over. And I'm now being asked to find the limit as x approaches 0 from the right of x over x. Well, what can I do? X divided by x, I can go ahead and cancel those two things. Again, notice that x is approaching but never quite equal to 0, so I'm allowed to cancel those two things. And so x over x becomes just 1. So this will be equal to the limit as x approaches 0 from the right of 1. So my function has just simplified to be 1 in the case that I am approaching 0 from the right. Well, what's the limit of a constant? That was one of our building block limits. The limit of a constant is just equal to that constant. So the limit as x approaches 0 from the right of 1 is just equal to the number 1. So the limit of my original function, absolute value of x over x, as x approaches 0 from the right, is equal to 1. All right, let's look at the limit as x approaches 0 from the left. Now keep in mind that if we are approaching 0 from the left, then x is going to be a value that's a little bit less than 0. That means that x is a negative number because it's smaller than 0. Over here on the right, let's remember how to rewrite the absolute value of x in the case that the number inside the absolute value signs is a negative number. So keep firmly fixed in your mind that x is a negative number. Perhaps think of x as being something like the number -6. So x itself is a negative number. Can I just take the absolute value signs away if x is something that is negative? Unfortunately, I cannot, because if I wrote absolute value of x is equal to x, and x is a negative number, for example, x is the number -6, that just won't work. The absolute value of -6 is not equal to -6. It's equal to +6. Well, how could I fix that up in the general setting here? If x itself is negative, I can make this expression positive by taking the opposite of my negative number. It would be like taking the opposite of -6, and minus a -6 would actually end up giving me a +6. So minus a negative number is actually a positive number. So the only way I can write that in general is to say that the absolute value of x when x is a negative number is equal to -x. Let's go ahead then and rewrite the expression that we have in the case that x is approaching 0 from the left, in the case that x is a negative number. In that case, the absolute value of x, we said, can be rewritten without the absolute value signs, but not just as an x, it has to be written as a -x. That way, minus a negative number will be a positive number. The denominator of my expression I just carry along, that's just x. But now if we simplify, what do we get? I have -x over positive x. When I cancel those two, I do not end up with 1, I end up with a -1. So this becomes, when we simplify, the same as the limit as x approaches 0 from the left, and -x over positive x cancels and gives me a -1. Well, this is now the limit of a constant. It's one of our building block limits again. Limit as x goes to 0 from the left of this constant, -1, is just equal to that constant. So my answer is actually a -1. The limit from the right of this function was +1. The limit as we approach x equals 0, as we approach 0 from the left of our function, turns out to be equal to -1. What about the overall limit? The limit as x approaches 0 of absolute value of x over x, we're approaching 0 from both directions. Well, the limit from the right existed and was equal to 1. The limit from the left existed, but it was equal to -1. These two limits, these two one-sided limits, are not equal to each other. They are not the same. They don't agree. And so what does that mean about the overall limit? The overall limit does not exist. So the answer to part C, all we can really do is say that the overall limit does not exist. Now you could also graph this function if you wanted to. First of all, what's the domain of this function? We have a division by x here, and I can see that I don't want the denominator of my expression to be 0. So just notice that the domain of the function is all real x except for 0. So we will not have any point on our graph corresponding to x equals 0. If you want to graph this function, it's not too hard to do. You just have to consider the case where x is greater than 0 and the case where x is less than 0 separately. So we could go ahead and simplify in exactly the way that we did up here when we were doing our limits, and we can consider what happens if x is greater than 0 and what happens if x is less than 0 separately. And remember, we can't allow x to equal 0. That is not in the domain of our function. When x is greater than 0, our function simplifies exactly the way it did when we were doing the limit as x approached 0 from the right. And remember that in that case, absolute value of x is just equal to x, because x is something that is positive. X over x reduces to 1. So this function is equal to 1 when x is greater than 0, positive. When x is less than 0, when it's something that's negative, again we can simplify exactly the way that we did when we were approaching 0 from the left-hand side through negative x values. We said in that case, absolute value of x is equal to minus x, and minus x over x reduced to negative 1. So this function reduces to negative 1 when x is less than 0. Well, what would these look like if I were to graph them? Remember that f of x, or y, equal to 1 is just a horizontal line at height 1 on our y-axis. And f of x is equal to negative 1, that means y is equal to negative 1. And that would again be a horizontal line of height negative 1 on the y-axis. So we would just graph the line y equal 1. That would be a line up here at height 1 on the y-axis, but we only want the portion of that line corresponding to points whose x-coordinates are greater than 0. In other words, we would only want the right half of that line. So I'm going to put an open circle right at x equals 0 and just pick the portion of the line, the horizontal line at height y equal 1 that corresponds to x-coordinates that would be positive. Y equal negative 1 looks like a line down here at height negative 1 on the y-axis. But again, we only want the portion of the line that corresponds to x-coordinates less than 0, in other words, to the left of 0. So I will put an open circle right at x equals 0 and just choose the portion of the line that corresponds to x values to the left of 0, smaller than 0. So the graph of this function, absolute value of x over x, looks like 1 when x is greater than 0 and negative 1 when x is less than 0. If I were to go ahead and try to find the limit of this function from the graph, I would do it exactly the way that we did in the previous example. I would choose values that are a little bit to the right of 0 on the x-axis, go up to my graph and over, and you notice that no matter how close I get to 0, the outputs are all approaching the same number 1 on the y-axis. So the limit from the right, that would be this limit up here, is equal to 1, just as we found algebraically. If I were to find the limit from the left, I would be choosing x values that are a little bit less than 0. Here I'd have to go down to hit the graph and over to the y-axis, and I would get the number negative 1. And no matter how close I get to 0, the outputs are all actually not just collecting around negative 1, they're equal to negative 1. So the limit as I approach 0 from the left is what we got before, negative 1. Still, the overall limit does not exist because as we approach 0 from both directions, from the right and the left, we get two different values. The y values are collecting around 1 from the right, negative 1 from the left. They are not collecting around one single number on the y-axis, and so the overall limit does not exist. So you can see that another way to do this problem would have been to graph it, but it takes a while to graph functions, and it's actually a bit faster once you get used to it to just do the problem algebraically. Okay, so let's go ahead and look at the last topic in this particular section, and that is an interesting limit theorem called the Squeeze Theorem. So that's what we'll be looking at next. And the Squeeze Theorem is just a theorem about limits that applies to certain particularly tricky limit problems that might not be able to be done in any other way. So let's see what the squeeze theorem says, and then we'll go ahead and apply it to a particular limit problem that can be done only with this theorem. So we're going to suppose the following. We're going to look at three different functions, f of x, g of x, and h of x. And we're going to suppose that for a certain interval of values around some value x equal a, we know that the outputs of the function g are trapped between h of x and f of x. In other words, g of x is something that's smaller than or equal to h of x, but greater than or equal to f of x. You might ask, well, what does that mean in terms of a graph? Down here I have a graph of f of x, and that's in black, and I have a graph of h of x. I've drawn that in blue. And if I'm telling you that g of x, that output value is between these two values, that means that the graph of g must lie between this blue graph of h and this black graph of f. If that's unclear, what we're really saying is that if you pick a particular x value, well, what is f of x? F of x you can get by going up to the black graph and over to the y-axis, or another way of thinking about f of x is that it is the height underneath the black graph right at the value x. That would be the same as the height on the y-axis if we were to go over the y-axis and say, that's what my f of x is equal to. So this height is exactly the same as this height. So here's f of x, it's this height underneath the black graph. H of x, by the same token, would be the height under the blue graph at the value x. So h of x is this height. And what we are saying is that g of x is the height under some graph that's in between these two, and the only way that could be true is if g of x is some function that's trapped between h of x and g of x. So it might wiggle around and do all sorts of things, but g has to be a function between those two. That way the height under this red curve, which is the height g of x, would be a height that's between h of x and f of x. So g of x has to have a height that's between h of x and f of x for each value of x in some interval around a. So g graphically is going to be some graph that's trapped between the blue graph h and the black graph f. Now what I want you to do is to also assume that as x gets closer and closer to a, f of x is getting closer and closer to L. In other words, we're going to assume that as x approaches a, the limit of f of x is equal to the number L. You can see that in the graph here. If you look at the black graph, that's the graph of f. As I get closer and closer to a from the left and the right, it looks as if the outputs are getting closer and closer to the number L. And so the limit as x approaches a of f of x is equal to L. And I've drawn it just with an arrow here saying that as x gets closer and closer to a, f of x is getting closer and closer to L. In a similar way, let's also assume that as x gets close to a, h of x is approaching L. In our picture here, we're really saying that as we get closer and closer to a from both the left and the right on the blue graph of h, the outputs, you can see, are again getting closer and closer to the single number L on the y-axis. So the limit as x approaches a of h of x, we are also going to be assuming that that is equal to L. So there are two assumptions. G of x is between f of x and h of x for each x in some interval around a. And we're assuming that the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of h of x is equal to L. Well, the question becomes, what would have to be true about g of x? F is getting closer and closer to L. H is getting closer and closer to L as we squeeze in on a from both directions. What has to be true about the outputs g of x as x approaches a from both the left and the right? Can you see from the graph, if g of x is trapped between f of x and h of x, what has to be true about the limit as x approaches a of g of x? Well, if I approach a from the right and I go up to the red graph of g and over to the y-axis, it looks as if the outputs are collecting around the number L. And if I approach a from the left side and go up to the red graph of g, it also looks like the outputs are collecting around the same number L. And so the limit as x approaches a of g of x is also equal to L. Up here we could say that f of x is getting closer and closer to L, h of x is getting closer and closer to L, g is trapped between those two things, and so it is also getting closer and closer to L. And that's the conclusion of the squeeze theorem if we know g is between f and h, and we know that the limit as x approaches a of f is equal to L, and the limit as x approaches a of h is equal to L. The conclusion is that the limit as x approaches a of g of x must also be equal to L. And that's really all the squeeze theorem says. It says if you have a function that's squeezed between two other functions that are both approaching the same limit of L, then the function that's in between must also be getting closer and closer to L. Well, let's go ahead and see if we can apply this to a specific example that couldn't be done in any other way than using the squeeze theorem. So we're going to go ahead and look at the example that is on the next page. And the example on the next page says, find the limit as x approaches 0 from the right of x times sine of pi over x. And by the way, the squeeze theorem works for the overall limit, if you have the limit as x approaches a from both directions, for limits from the right, and for limits from the left-hand side. In this case, we have a limit as x approaches 0 from the right-hand side. Now, this is kind of a weird function. We've actually already talked about the function sine of pi over x, and you might remember that in an earlier section, we found out that the limit as x approaches 0 from the right of just sine of pi over x did not exist. I'll put does not exist. We found that because we graphed this function, and we found that as you approach 0, this function starts oscillating more and more rapidly between the values of 1 and -1. And so as you approach to 0 from the right-hand side, we did not have y values that were collecting around one single number on the y-axis. In fact, we had an infinite number of y values that we kept hitting between -1 and 1, and therefore we said that limit did not exist. Keep that in mind. We have a slightly different function now. We have the function x times sine of pi over x. So you might say, okay, well, let's go ahead and find this limit by using the product limit law. The product limit law would say that I can go ahead and break this up into the limit as x approaches 0 from the right of the first function, namely x, and then multiplying that number by the limit as x approaches 0 from the right of the second function, sine of pi over x. This limit we can actually find. It's the limit of a polynomial, or you can just think of it as the obvious limit. As x approaches 0 from the right, x is going to be approaching 0. It's just the obvious limit, or you can think of x as a very simple polynomial and use direct substitution. Unfortunately, this limit does not exist. And remember, for that product limit law to work, both of the individual limits in the product have to exist. So unfortunately, we can't use the product limit law. And that's because one of the limits doesn't exist. And in the product limit law, we're assuming that the limit of f of x and the limit of g of x both exist. Then you can go ahead and say the limit of the product is the product of the limits. But in this case, one of our limits does not exist, and that was proved in the previous section. Well, does that mean we give up? Just because the product limit law doesn't get us to an answer, it doesn't mean that there isn't an answer and that we can't find this limit or that the limit doesn't exist. It may or it may not. Let's recall that sine of anything has to be a value somewhere between 1 and negative 1. So sine of anything we plug in can't be more than 1, and it can't be less than negative 1. No matter what value you plug into the sine function, it's bounded between 1 and negative 1. So sine of pi over x, since it's sine of something, has to be a number between 1 and negative 1. It is bounded in size. Well, we're really not interested in any limit that involves just sine of pi over x. What we are really interested in is the limit as x approaches 0 from the right of x times sine of pi over x. So what I'm going to do is try to transform the middle of this compound inequality to involve the function that we're trying to find the limit of, namely x times sine of pi over x, and I'm going to do that by multiplying my whole inequality through by x. So I'm going to multiply through by x. Now, generally when we multiply an inequality through by something, we want to be sure that we're multiplying through by something that is positive. If x were something that was negative, we would actually be in trouble, because if x were something that's negative, remember you have to switch the direction of the inequality signs. Well, we are going to be finding a limit as x approaches 0 from the right. So remember, that means that x is going to be something that is greater than 0. That means that x is something that's positive. So note that for the limiting process that we're going to end up doing, x will be greater than 0. In other words, x is going to be something that is positive. That means that I can multiply this inequality through by x and keep the inequality symbols in exactly the same direction as long as my x is something that is positive, greater than 0. So let's multiply through by x. I have to multiply each part of the inequality through by the same thing. Negative 1 times x is going to give me minus x. Here, when I multiply by x, I'll get x times sine of pi over x. And 1 times x is going to give me x. And as long as my x is greater than 0, I can leave the inequality symbols in the same direction. I don't have to reverse them. What I would like you to do next is to think about what's the limit of this function as x approaches 0 from the right. So down here, maybe we can write it down. We're finding the limit as x approaches 0 from the right of the expression minus x. Well, what type of function is minus x? Notice that it is a polynomial. And because it's a polynomial, remember we get to use direct substitution to find this limit. And so I just replace x with the number it's approaching, namely 0, and I get that this limit is minus 0, which is the same thing as just 0. Let's also find the limit as x approaches 0 from the right of the function that's on the right side here, which is x. That's also a limit I can do. It's the obvious limit, or again, you could say x is a polynomial, so I get to just use direct substitution. So the limit as x approaches 0 from the right of x, I just replace x with the value it's approaching, and it is approaching the number 0. So as x approaches 0 from the right, this function is getting closer and closer to the number 0. And as x approaches 0 from the right, this function x is also getting closer and closer to a limit of 0. So I have a function g of x that is trapped between two functions that are both approaching the same number, the same limit, L, we said in general on the previous page. In this case, my L is equal to 0. These are both approaching the same number, 0, and I have a function that's trapped between two functions that are both approaching the same limit. What does that mean by the squeeze theorem? By the squeeze theorem, the function that's trapped between two things that are both approaching 0 must also be approaching that same number, 0. That's really by the squeeze theorem that we talked about on the previous page. The function that is on the left side of this inequality is approaching 0. The function that is on the right side of this inequality is approaching the same limit of 0. So the squeeze theorem is going to tell me that the limit as x approaches 0 from the right of this function that's trapped between them of x times sine of pi over x, that limit must also be equal to 0 by the squeeze theorem. That was the limit we were asked to find. The limit as x approaches 0 from the right of x times sine of pi over x. So although we couldn't use the product limit law, we could use the squeeze theorem, and that allowed us to find an answer of 0. This is a limit that could not be done in any other way except by using the squeeze theorem. So the squeeze theorem is helpful in oddball cases. It'll also be helpful in some of the theorems that we'll prove later in the course. By the way, here's a graph of what this weird function sine of pi over x looks like. And let me just show you that graph. I believe it's on the next page of your handout or booklet. This is a weird looking function. It looks kind of like the function that we graphed when we just graphed y equals sine of pi over x, but remember that kept waving up and down between 1 and -1. This one has a sort of a variable amplitude that would look like the line y equal x or the line y equal -x. So unlike y equals sine of pi over x, which has a constant amplitude of 1, this function has a variable amplitude of x. And what does that mean? It means that the function does wave up and down. It oscillates more and more wildly as I get closer and closer to x equals 0 on the x-axis, but the amplitude of the function attenuates and gets smaller and smaller and smaller. So we were looking at the limit as x approached 0 from the right of this function. And you can see then from the graph that as I approach 0 from the right, if I pick a particular x value, I go up to the graph and I go over to the y-axis. And as I pick different x values, I do get different outputs, but because the amplitude of my function is getting smaller, these outputs are sort of waving up and down above and below 0 on the y-axis, but they are slowly collecting, or perhaps I should say quickly collecting, around 0 on the y-axis. So they're going above, below, above, below, above, below, but I'm hitting values that are zeroing in on the value 0 on the y-axis. So the limit as I approach 0 from the right of this function, the y values are collecting around one single number. They're getting closer and closer to the number 0. So this limit does turn out to be 0. It actually turns out that if you approach 0 from the left, and the limit as x approaches 0 from the left of this weird function, you would also get 0 as an answer. And so the overall limit as you approach 0 from both the left and the right of this function would have an answer of 0. Okay, let's go ahead and look at one last example. And this is another example that is difficult to do unless we can involve the squeeze theorem. So let's think about this function. It's a really weird one. I said let g of x equal x squared if x is an irrational number and 0 if x is a rational number. Remember that a rational number is anything that can be written as one integer a over another non-zero integer b. So something like the number 2/3 is a rational number. But there are lots of numbers that are irrational. A typical irrational number would be something like square root of 2. It cannot be expressed as the quotient of one integer divided by another integer. Pi is another irrational number. Remember, irrationals have infinite, non-terminating, non-repeating decimal expansions, whereas a rational number, if you write it out, will either have a terminating decimal expansion or a repeating decimal expansion. For example, 2/3 is 0.6666, where the sixes go on forever. It has a repeating decimal expansion. Well, let's think about what the graph of this function looks like. If my input, I should say, is something that is an irrational number, such as root 2 or square root of 6 or pi, I'm supposed to use this rule for g of x. So for all of the x values that are irrational, and there are lots of them along the real number line, this looks just like the function y equals x squared. And what does y equal x squared look like? It's a parabola. It opens upwards. The vertex is at 0, 0. It's the standard parabola that you usually learn about in your beginning algebra class. And so it looks something like this. Let's see, 0, 0 is on the graph. Well, I shouldn't say 0, 0 is on the graph because it's only equal to x squared if x is irrational. But if I were just to draw that parabola, it would look something like this. It would be a parabola that opens upwards. But that would be if I were drawing the parabola for all real numbers x. I am only supposed to use this rule, this graph, when my x is something that's irrational. And it turns out that there are an infinite number of irrational points on the real number line. So in particular, if we consider the x values, say, between -2 and 2, there are infinite number of points along here that correspond to x values that are irrational. Of course, there are also an infinite number of points along here that correspond to x values that are rational. So sometimes we sort of graphically show this by saying, well, it looks sort of like a bunch of dots along this parabola. Let me erase this. And I have a dot only at each x value that is an irrational number. For example, square root of 2 is on here somewhere, and I would have a dot along this parabola corresponding to x equals square root of 2. So it's a weird sort of function. There are actually an infinite number of these dots that lie along this parabola, and we only pick out the points that corresponds to x coordinates that are irrational. Now, when x is rational, we have the function y equals 0. What would that look like if I were just to graph it and ignore this fact that the inputs have to be rational? It would be a horizontal line that crosses the y-axis right at the level 0. It would actually lie right along the x-axis. But we only want to draw the points along this line to pick out the ones that correspond to x coordinates that are rational numbers, things like 1/3, 2/3, 1, which can be written as 1 over 1, 2, which can be written as 2 over 1. So it would actually look like sort of a line, but only a bunch of dots, and each of these dots or points corresponds to an x coordinate that is a rational number. So we pick out an infinite number of points along the line y equals 0 and an infinite number of points along the parabola y equal x squared, and we choose a point on this line y equals 0 whenever the x value is rational. However, we choose a point along the parabola whenever the x value we're plugging in is something that is irrational. A very weird looking function. Well, let's see if we can do the following problem. In part B, we're asked to find the limit as x approaches 0 of g of x, and we're asked to prove our answer. One way to do this problem would be to do it graphically. So you might stop the camera, the video, for a moment and see if you can find the limit of this function g of x, this thing that we've just graphed, from the graph. And then we'll go ahead and try to do it proving our answer. And we'll have to think about how we can do that. Okay, I'm hoping you've had a chance to think about how to find the limit as x approaches 0 of g of x from the graph. And remember, we're looking at the limit as x approaches 0 from both the right and the left. If I were to approach 0 from the right-hand side, well, what would be happening, it would be sort of weird, as I approach 0 from the right, whenever I hit an x value that is rational, I would be right on this line, and so I would get an output value of 0. If, however, I choose an x that's right next to it that is irrational, I would be up on this parabola, and when I go up to the graph and over, I would hit a value that's somewhere on the y-axis here, on the positive y-axis. But notice that the closer I get to 0, I will either be hitting 0 itself if my input is rational, or I will be hitting the parabola if my point is irrational. But as I get closer to 0, these parabola points also get closer in height to 0. So I hope you can convince yourself that as I approach 0 from the right, I'm either getting 0 as an output or a y value on the parabola that is marching down and getting closer and closer to 0. The limit of this function, at least from the graph, as x approaches 0 from the right, is equal to 0. Now, let's look at the limit as x approaches 0 from the left. Again, it's weird. If I plug in a rational number, such as -1, I would choose a number right along the horizontal line, y equals 0, and so I would get 0 as an output value for my y. If, however, I choose something very close to 1 but that is irrational, I have to go up to the parabola and over to the y-axis. So I'm going to either be getting outputs that are equal to 0 or outputs that are successively getting closer and closer to 0. And so the limit of this function as x approaches 0 from the left would also be equal to 0. That, though, is not really a proof. That's an argument from the graph. If I wanted to prove that the limit from both the left and the right is equal to 0, the only way I can really do that is to employ that squeeze theorem that we talked about. How do I employ the squeeze theorem? Remember that g of x, my function, is either equal to x squared when my input is irrational, or it is equal to 0 when my input is rational. That means that g of x is either equal to this function or it's equal to this function. One way of writing that would be to say that g of x is less than or equal to x squared or greater than or equal to 0. So g of x is either equal to this function x squared or it's equal to 0. That means that I could certainly say that it's between these two functions. It's less than or equal to x squared because it's either equal to x squared, or it's greater than or equal to 0 because the other alternative is that it is equal to 0. So I could go ahead and say, yeah, the value of g of x is definitely less than or equal to x squared or greater than or equal to 0 because it's either equal to x squared or it's equal to 0 for any particular x value that I choose, and it just depends on whether x is an irrational number or a rational number. So I could go ahead and make this statement: g of x is between the function 0 and the function x squared for any particular value of x. Also, we can ask ourselves, well, what happens to these bounding functions as x approaches 0? If I were to find the limit as x approaches 0 of this function on the left, 0, well, it's the limit of a constant. It's one of our building block limits. So the limit of a constant is that constant. So this function is just staying fixed at 0. If I were to look at the limit as x approaches 0 of the function that's bounding g of x on the right, well, what kind of function is that? It is a polynomial. So how do we find the limit of a polynomial? We get to use direct substitution. And so the limit as x approaches 0 of x squared is just 0 squared, or 0. So this function that is bounding g of x on the right is approaching the same limit of 0 as x approaches 0. Now we can employ the squeeze theorem because we have a function that's bounded between two functions that are both approaching the same limit of 0 as x approaches our a value, 0 in this case. And what does that mean about this function that's squeezed between two functions that are both approaching 0? It means this function must also be approaching 0 as x approaches 0, and that's by the squeeze theorem. So formally then we could say the limit as x approaches 0 of g of x must also be equal to 0 by the squeeze theorem. Sometimes abbreviate squeeze theorem that way. And that's the answer to our problem, and that's a rigorous proof of the fact that the limit as we approach 0 from both the right and the left of this function does appear to be equal to 0 from the graph. But now we've proved it using the squeeze theorem. Well, that's it for this particular section, and in the next video we will be talking about a new concept called continuity of a function.